Okay, are we ready?
Ready.
Sweet. Okay, so me and Creighton were thinking this is also an invention. Well, we got the idea from Greg Hurd over in the room next to us, and he was talking about how if you charge two wires, one with a positive and one negative, then you're going to get an electric field. And if you put that in water, you can actually measure the electric field. And so me and Creighton thought, well, let's try and map out and investigate all the different things in deeper and deeper context about the electric field. So what we did is we got an electrophoresis chamber from the old biology stuff that they got. And so this was open, and then we filled this chamber with water, and then we make columns. And so this would be column 1, 2, 3, etc. And then we did rows going across. And so we said this was row 1, 2, and 3. And then we'd also thought we'd examine the depth. So if you're starting at wire level, how will the electric field change as you go up? Because what we initially thought, and what you think of, if you have two wires, then you think it would go something like that. But then it also kind of like curve up. And so we thought, well, let's see if we can actually get those kind of results. And so the wires were right here and right here. And so we took a power source and then hooked that up so this side was positive. And then we hooked it up so this side was negative. And we took a voltmeter and we would place it in different parts on the actual, in the actual chamber. So we would stick it in at a certain depth and then continuously go over and over and over and over. But anyway, I guess I'll get to the hypothesis first. So we thought that, well, initially, if you're going to go through something other than prime, like a vacuum, that there's going to be a voltage drop anyway. So we predicted that there would be a voltage drop in our system. And then also, if we measure the voltage in the y direction, then this distance wire from increases, the voltage will decrease. So if you're starting and measuring this depth around wire level, as you go up, the magnetic field, or the electric field, did I say the voltage? The voltage will decrease. And then next, in the x direction, as the distance from the wire increases, the voltage will increase. So if you're measuring the voltage from this place to two place, because we all know that voltage is the potential between two areas, wherever you're measuring it, it'll be dependent on wherever your meters are. And so if we put it right here, this is where we're going to get maximum voltage. And then as we decrease and go to each column, it was going to get smaller and smaller and smaller. And then every row that is measured and tested, it should produce roughly the same results in each subsequent text. So if you're thinking about like a parallel plate capacitor, that you're going to get a voltage change as you go this way, right? But if you move perpendicular to the field lines, then you're not going to get any voltage change. It's going to be equipotentials. So we thought as we moved from row to row, we were going to get the similar results. And then in 5, the electric field will be constant as the x direction and distance increases. So the electric field line, or whatever we're thinking, because we all think we only use electric field lines so we can have an idea of how it looks. Because they're not actually there, it's just how we are able to conceptualize the forces and everything. And so it's going to be in the x direction, this way and that way. The electric field is going to be constant. But in hypothesis 6, if you go up, then it's going to decrease. And the electric field is going to be strongest right here, weaker right here, weaker, and weaker. And so I kind of outlined the procedure already. And so here's kind of a picture of our whole setup. If you guys, do you need me to zoom in a little bit? Or, so row 2 is actually what we were calling row 1. And so we would measure it going over and over and over. And we put it on continuous data collection. So we could go like set it and then holding this one on the negative side as the anchor point, go over, 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 over. And then once we got all the way down to 0, the distance was 0 between the 2 meters, we pulled them out, set them in at the next depth level. And so that was going to be H2, height from the wire up. And that was 0.02 meters. And then we do the same thing, and then we did that for every row so we could get tons and tons of data. And so I drew the diagram. And then this is some of the like how the data was looking. And so, for example, the blue line was, or the blue data was our row 2. And so if as you're going up and up, these are different depths. So each peak is a different depth. And so this is the smallest, this is depth of 0 all the way down at the bottom at wire level. And then this is all the way at the top at 0.03 meter height from the wire level. And as you go down, that's us going over and over and over in the x direction and putting the meters closer together so you can see it going decreasing. And then it's also increasing as depth increases, but it's also kind of an exponential fit. Is everybody following? Okay.
So that looks like a graph versus time, but time is just a way for you to separate different experiments.
Yes. And so what we did is we would pull each data point would be, this is a data point, that's a data point, that's a data point, that's a data point, that's a data point. And then here is an example of some of the data that we got. And so this is, we organized it into 2 separate graphs so we could check out the differences in height, and then we could check it in the y direction, and then the voltage differences in the x direction. So this is our results in the y, and then these are the results in the x. And they're a lot more seeable once I move to the graphs. And so we thought, so if we're going to get electric field, what we want to do is we want to put voltage as a function of distance, because we all know that electric field is equal to a volt per meter. And so in the x direction, we have a clear, without linearizing anything, it was a linear relationship as we move the probes over and over in the x direction. And so as the distance increased, the electric field would remain constant. And so at the and these are separate. So this is row 1 for right here. And then this is at the very bottom, so a depth of 0 meters. And then as you go down, it's showing different slopes and different electric fields. So the strongest electric field was 32.26 volts per meter, and then our weakest was 26.65 volts per meter. And then similarly, all of the different rows in the x direction were showing the same results. And then this just kind of is able to show how the slopes are very similar, 33, 32, 32. And then they would decrease as the height got up, or increased. And then y direction graphs, we were a little thrown off by, because we expected kind of a different change, but it was more of an exponential fit as the height increased. And so this is just saying how we were able to linearize it. And then our linearization was right here. And so we had to take a volt per 1 over a meter squared, so volt meters squared. So we said that was the rate of change of the electric field as height increases. And then we were getting some crazy stuff for all the different rows. And so they're all listed in the same way as we are going our height. So starting right here, we took it as it goes up, up on each column. And so we're getting fits of rates of change that were kind of a little varied, but in the middle data sets, like this is 8, and then that was 7, 7.8, which are relatively close. and then these were all similarly alike. So we were thinking that maybe there was concentrations or like error in the wires themselves, because the wires were coiled a little bit in our setup at the ends, and so we thought that could have affected that. And then moving on, we thought we'd try the electric field as the slopes that we got from our x direction graphs, so we could see the electric field in the y direction. And then we're again a little surprised because our fit, these were the two outside rows, so this row and then this row, and then the center one had a definite steeper slope and decrease as height increased. So we are not entirely sure what that could have been. We could just think that it was the differences in because we know that field lines are quantized, or we're thinking that they're quantized. So differences such as that. And then we also try to give it a Gaussian fit to see, since it was like random, and since there really aren't technically electric field lines, to see maybe that it's a little bit more random than we thought. And then these are all our different linearizations. And then our error, we just did the x direction, and at the very bottom our error was quite little, 6.27, 4.49, 3.85. And we did that by taking accepted values of putting the voltmeter on each wire separately, and then taking the voltage drop. And the voltage drop, we put it in 10, we set the power source to 10 volts, and in the liquid it dropped all the way down to a little bit above 6, so 6.149 roughly. And so we said a 40% drop. But as the height got up, we thought the error would get greater because it wasn't going to be the theoretical one that we would always say in a situation